Hey guys, today we're talking about something that's very common sense, very useful, and good stuff. This is about work and energy. You know that work is getting something done, and you know that it takes energy to do that, that energy is what enables work. And so that's what we're talking about here in this little section. Here's kind of a formal definition work, using a force to move an object, and the formula right there is the first formula that we want to write down here. Work equals force times distance. If I take a force of 20 newtons and I move something a displacement, a distance of 3 meters, then I would come in here and say work equals 20 newtons times 3 meters. 20 times 3 is 60. And there's Newton meters, and it's generally that simple. That Newton meter becomes a new unit called a joule. So right here, we would just replace that with 1 joule, Joule, where 1 joule is 1 Newton meter. It's an abbreviation. It's a shorthand. We're remembering James Prescott Joule, who was interested in energy and how much heat came out of reactions and stuff like that. So that's pretty easy to do. Notice up here that there is this little caveat. The force is constant and parallel to D, to the displacement. So I think our book is probably using X here instead of D. But whatever it's using, the displacement and the force give us the amount of work. Notice some interesting things here. If I do not move the box, if the displacement is 0, then the work is 0. So that's kind of interesting. I could kill myself pushing on a mountain, but until I moved the mountain, I didn't accomplish anything. I did 0 work. Here's another interesting idea. If I had a box right there and I moved it over there, then the displacement, like before, might be 3 meters. And maybe I pushed 20 newtons that whole way and I would get 60 joules, just like we did. But displacement is from beginning to end, right? So if I took this path right here and set the box down right there, the displacement would still be 3 meters, and I used 20 newtons all along that way. It's still 60 joules of work from point A to point B. We're measuring from beginning to end here. Work is kind of funny that way. You would notice here that some of these works could be considered in the opposite direction or negative. So you've got some positive work, and that's kind of canceled out because we were pushing in the opposite direction, and then so on and so forth. But the work is said to be path independent. It doesn't really rely on which path we take. It's the same amount of work to move something from point A to point B. Okay. Here are a couple extra little things that are worth noticing. We've already talked about this one. The work is equal to force times distance when force is constant and parallel to the displacement. So you can see that this guy, he's pushing up the hill, and the box is going to move up the hill, and perfectly fine just to multiply those two numbers. No big deal. If the two forces are not parallel, then technically we should do a dot product with the vectors. And that's given here. Another way to write that would be the first vector dot the second vector dot, like that. So it's a way to multiply vectors that we haven't really talked about here, but you could FD cosine theta would give us that amount of work. The easiest way for us at our level to think about that is that if I take F cosine theta when I'm pushing down at some angle, see there's F right there, and if I multiply by the cosine of the angle, well, then I'd get the component of the force that's in the direction of the displacement, and I'd want to multiply that. This guy is pushing to the right and down on that lawnmower, and the part where he's pushing down doesn't accomplish anything. It just makes the ground push back up harder. So if I do that F cosine theta, don't worry too much about that one. This third one here, you can worry even less about it if the force is changing. If in time, I start off pulling very softly and then I pull harder and harder and harder, that's a changing force, and there's a process called integration using calculus that adds up the effect of all of that force over the distance to give us work. Okay, everything that we need is this guy right there. Okay, I don't know of any times, this would be the next easiest one to do. But again, just get the component of the force that's in the direction of the displacement and use that. Don't worry about the bottom one at all. Kinetic energy is the energy that a moving object has. There's several ways to think about this. If I took a baseball and threw it and hit a window, then that baseball would transfer energy to the window and would probably break the window. It would have enough energy to break the window. Where did that energy come from? Well, because it's moving, it has that energy. The energy of a moving object is called the kinetic energy, and it's given by this formula. The kinetic energy is equal to 1/2 the mass of the object times the velocity squared. So this is an important number that we use all the time with moving objects. Notice here, if V equals 0, if the object is not moving, then the kinetic energy equals 0. Okay, every everyday object that we can think of has mass, so we won't really go into there. You could argue about light and stuff like that, but that's a whole different discussion. So let's not worry about that. Here's another way to say this. This could also be thought of as the work required to get an object moving, right? If I threw that baseball, then I had to put a force on the baseball over some distance. It took work to get the baseball moving, and now the baseball has that energy. I had the baseball, I did work on the baseball, and now the baseball has the energy. So we're kind of handing energy from one place to another, and it moves, it transforms, from one form to another, and that's one of the interesting things about energy. If I have energy, I can do some work, or if I do some work, sometimes I can generate some energy. So they go back and forth, they're hand in hand, and we'll see more about that in just a little bit. Here's a little example. I don't think you really need this, but let's try it anyway. Here's that baseball I was talking about. Let's say it's 1 kilogram, and I throw this thing at a velocity of 4 meters per second. Okay, you can see how easy this is. The kinetic energy is 1/2 the mass times the velocity squared. That'd be 1/2 times 1 kilogram times 4 meters per second. That gets squared. 4 squared would be 16 times 1 is still 16. Half of that would be 8. And my units here would be kilogram meter squared. I'm going to write that meter over second squared, which I will write as second squared. And then just kind of to show you how this turns back into our units, if I take this kilogram and that meter and that second squared, then that would be a Newton. And I've still got that meter left on the outside. And a Newton meter, of course, is a joule. So we're back in joules. The unit of kinetic energy is joules. The unit of work is joules. Everything comes out in joules here with energy and work. So that's how you get there. And you could take the joule back apart if you needed to, turn it back into a kilogram meter per second squared, and cancel stuff, whatever you needed to do with it. But that's the energy of a moving object. Here's another kind of energy called the potential energy. Several ways you can think about this that are listed here. Sometimes people say the potential energy is energy by virtue of position. For example, if I had a book and I picked that book up from here to there, obviously I did some work to get it up there, right? But now that that book is up there, where did the energy that I used to raise it up there, the work, the energy that did that work, where did the energy go? Well, it's stored there. All right. So another way to think about this is stored energy, stored work. A third way, the potential to develop kinetic energy. If I've got the book up here at the top and I turn loose of it, then it changes back into kinetic energy. It falls. Gravity accelerates that thing. And so my work is kind of stored up there. Any way you want to Want to think about that. By virtue of being up here, up in the air, it has this gravitational potential energy. If I turn loose of it, then the thing has the potential to develop kinetic energy. Or alternatively, as I raised it from here to there, I did work, and that work gets stored as energy, which we call potential energy, or more specifically gravitational potential energy. There are other kinds of potential energy, for example, a spring. If that's supposed to represent a spring, and I take my finger and I compress the spring down, I think you'll agree that I did some work there, right? I used the force of my finger and displaced the end of the spring, so that's work. Where does that work go? Well, it's stored in the spring. That would be spring potential energy, another kind of energy. Okay. Here is the formula for that gravitational potential energy. The gravitational potential energy is equal to mass times gravity times height. You can see that that works out. Here's a big rock. I'm going to pick this rock up. How much force would I have to use? If I calculate the work it would take, work equals force times distance. So I say, well, what force would I need? Obviously, gravity is pulling down, and I need to put this upward force. The force that I need to exert on the rock is equal to the weight of the rock. So I'm going to replace force with mg, and then I want to raise the rock from here, let's say up to there, some distance h. And so there's the force. The distance is h, and I get mgh. That's the amount of work to raise the rock. And guess where that work goes? It goes into the potential energy of the thing. So this is equal to the gravitational potential energy right there. We could put some numbers in. Let's do that. Let's say I had a 4 kilogram rock. G is 9.8 meters per second squared. And I raised that thing 2 meters like there. Then I would have 4 times 9.8 times 2. The number is 78.4. And looking at the units one more time, you can see that if I take this kilogram and that meter per second squared, that's going to make me a Newton. And then I've got this leftover meter, which would be right there. So I'd have 78.4 joules. We're back in joules again. Here's how to do the spring potential energy that I mentioned. We compress the spring down, or the same thing if we stretch it or compress it, it doesn't matter. Then the work is given by this formula right there. This actually takes calculus to do. Well, one way to do it is with calculus, but so I won't derive that. You can kind of look at the area of this triangle over here. The force that it takes to compress that thing is going to get harder and harder, right? So it's going up at a slope like that. And if I displace it some distance here, then I could find the area underneath that curve, and that would be equal to the work that I did there. Calculus kind of does the same thing. It finds the area under a curve, and so that way I mentioned that you don't need to worry about, all right? But it's a handy way to find the area under a curve, and that's where that formula comes from. K here is called a spring constant. A spring constant is a number that tells how strong the spring is. So obviously if this is a big truck spring, off of a truck suspension system or something, then I'd have a big number. If I pull a spring out of a little ballpoint pen, that's going to be a really wimpy number. It's just a number. Typically the units of K would be newtons per meter, meaning how much force do I have to put on it to compress at a certain distance. That will also turn out in joules. This whole potential energy thing will be measured in joules right there once we do it. And we could multiply that out, but I don't know of any places we really have to do much with that. So a couple homework problems, I think. Something about a train that bumps into a spring and comes to a stop. Well, the train had kinetic energy, where did the energy go? It went into the potential energy of the spring. So we'll say more about that in a minute. Check this out, though. Here's a box on the floor. I've got to do some work to raise this thing up. And so here's the box initially, point A. I do some work. That work is equal to force times distance, which we saw before was equal to mgh. And now the box is up here at point B. And guess what? All that work that I did got stored as potential energy. And we saw that to calculate the gravitational potential energy, it's just mgh. And if I drop the box from point B, then as it falls, the potential energy turns into kinetic energy, right? So here's that path, and potential energy turns into kinetic energy. At that bottom point, the potential energy is equal to 0, and the kinetic energy would be equal to whatever I had before. So it's equal to the potential energy at the top, or it's equal to the work that it took to raise the lifting work that I had to do there. It's the same number. I don't get anything for free. All right, there is no free lunch in this universe. If you want to raise the box from there to there, that is going to cost you some energy. But once you've paid that energy is still there, and you can use it in other ways. Here, I could turn it into kinetic energy. I'm thinking about a pile driver. When they're building a big building, they have a crane, and they lift up a great big heavy thing with the crane, and then they drop it, and it does some work. It drives the pylon into the ground. And this is the same kind of thing. So I do some work, raise the pile driver, drop it. It develops kinetic energy from the stored potential energy from the work that I did, and then it does some work. Nothing ever goes away. It's all still there. I don't get anything for free, and it doesn't go away. We call that idea conservation of energy, and this is a really big deal. This is such a big deal. We believe in this thing and rely on this so much that we call this the law of conservation of energy. And a law is a big deal. We have lots of theories in science where we think we know what's going on, but this is one of those that we really lock in on and say, yes, I really believe this to be true. There's several ways to state this, which are given here. Number one, energy cannot be created or destroyed, only converted from one form to the other. So let's say that you can take this back as far as you want to go. The sunlight comes, right? The sun has a whole lot of energy. It spews some of that energy in the form of light out through space. That light makes it to Earth, right? And so that's energy coming in. That energy is going to warm up the atmosphere. It's going to warm up the Earth. It's going to cause plants to photosynthesize and grow. It's going to, animals can come along and eat the plants. That energy runs everything, and it can't be created. It can't be destroyed. It was sunlight. Now it's light. Now it's warmth. Now it's grass. Now it's cow. Now it's person who ate the hamburger, right? It just changes from one form to another, and it's all still there. Second way to state this, kind of the same thing, energy is constant. The amount of energy in the system is fixed. If I want more energy in it, then I have to add more energy. I don't get that for free. Here's kind of a nice way. This is, again, kind of the same thing, but the energy at time 1 equals the energy at time 2. Well, that's a mouthful. This little thing right here says that really nicely too, right? So, this guy is where we want to start a whole bunch of our problems for this chapter. Let's think about a roller coaster, right? Kind of classic problem. Here's a roller coaster. The cart's up here. It's a nice, pretty day. You're screaming your head off. Wah! And up here at the top, you have a whole bunch of potential energy. And then as you move down, you lose that potential energy. Remember, potential energy was equal to mgh. As my h gets smaller, my potential energy gets smaller. So down here at this point, then I have less potential energy. Well, where did that potential energy go? It has to go somewhere. It went into kinetic energy. So this converts over to kinetic energy equal to 1/2 mv squared. And I can say, well, here's point 1, there's point 2. I know I don't get anything for free, and I know I don't lose anything, so the energy at point 1 has to be equal to the energy at point 2. And if I'm only considering potential energy and kinetic energy, then I can say, well, at point 1, I would have these two right here. This would be the potential energy at point 1, and this would be the kinetic energy at point 1. And then over on the other side, I've got the same thing, but you see that the subscripts are different. So this would be the potential energy at point 2, and this would be the kinetic energy at point 2. And I can just set those equal to each other. That's the same number. So that's a good starting place. Here's a better picture than my little doodle, like you can see. But this actually has some numbers in it too, as well. So you can see that up here at the top, the height is 25 meters, and the velocity is 0. When the velocity is 0, that means that the kinetic energy is equal to 0, right? And so if I put V1 equals 0, here's point 1, right? And then I pick any other point I want for point 2, but at the top V1 was 0. That one crosses off. Sometimes these terms cross off, and I don't have to have all of them, but it's good to just put them all down and then see what you have, cross out what you don't need. This is the formula that generally we start with when we're doing these things. So 9 times out of 10, you see an object at 2 different points, just write that whole thing down, cross out whatever you don't need, and it'll be fine. Let's find the, eventually the cart makes its way over here. We'll call that point 2. Okay? I'd like to know the, let's say the velocity at that point. So we're going to find V2. We notice that the height there is, we've dropped 20 meters. So I'm still 5 meters off of the ground. So I don't care for the way they've done this picture, but I would prefer that they come in down here at the bottom and say, well, this is 25 meters up, and then this would be 5 meters up above that. But whatever. I'm going to change this and say height equals 5 meters. You can call any point you want 0. But then you have to have negative signs and all that, and we don't want to do that. So as I do this, H2 is equal to 5. H1 we said was equal to 25, and we're looking for V2 right there. You can see that there's only one unknown. Actually, there's 2, but one of them is mass, isn't it? And look how I've got mass in every, it's right there. It's right there, it's right there, it's right there. If I've got it everywhere, I can cancel it out, right? I could factor it out on the left and factor it on the right, and then when I divide on the left, it would divide the one on the right. When it's in each and every term, you can just cross those guys out. Okay? So I don't even need the mass. The mass doesn't matter. It's irrelevant. It's the same the whole way. Now, if a kid falls out of the roller coaster, or something, I guess that would change things. But here, if I want to solve that thing for V2, I could take this term, subtract it from both sides. So then I'd have mg, well, let's see, we got rid of the m, didn't we? I'll erase that in just a second. GH1 minus GH2 equals 1/2 V2 squared. And I want to get rid of this guy right there, okay? And we wanted V2, so now I need to multiply the whole thing by 2 to get rid of that 1/2. Right, that took care of that thing, and that would leave me V2 squared. I don't really want V2 squared, I want V2, so I could take the square root of that thing right there. And it'd be lovely to have a little bit more room here, but I think I can make this work. 2 times 9.8, let me put a bracket there just to H1 was 25 minus 9.8 times 5 And that's what we're trying to do here. So I'm going to do square root of 2 parenthesis 9.8 times 25 minus 9.8 times 5, and I get about 19.8. That's a velocity. If you chased all the units, I didn't have room to put them in there, but we'd be moving 19.8 meters per second right there. Why? Because the energy is there. Because I have to account for all of that energy. It can go into this form, that form, whatever, but it's got to still be there, and it's got to be the same number I started with. And we call that conservation of energy. Here's something that comes out of conservation of energy. This is the work energy theorem. And so I want you to look when you do homework problems. If you see an object at two different places, the same object, one object at two places, you need to be thinking about conservation of energy. One object at two places, all right? And you can see the car down there. See what I'm talking about? The car is here, and then a little bit later on it's over there. One object at two different places. In this chapter, that's probably a conservation of energy problem. I don't get anything for free. I don't lose anything. It's all still there. In this one, this comes straight out of conservation of energy, but it's kind of a special case of that, and we call it the work energy theorem. The work energy theorem says if I do work, right, here's the car engine that's pushing this car forward with some force F, and it does that over a distance x. The car engine is doing work right there. And in order for the car engine to do work, it had to get the energy from somewhere. And of course here it's getting the energy from the gas tank. So the chemical energy of the gas, you burn that, it turns into heat energy, and then the heat energy does work on the pistons, and that gets transferred into the motion of the car, right? I did some work. Work, energy, kind of two different forms of the same thing. That work gets changed into a change in kinetic energy. That work is used to change the kinetic energy from one speed to another speed. The work has to go somewhere. It can go into potential energy. This is a flat road, right? So there's no change of potential energy there. But so the only place that work can go is in, assuming no air resistance, is into changing the kinetic energy of the car. So that's kind of an interesting thing right there. Look for this guy, and anywhere that you see anything about force and time, force and distance here. If they're talking about force and distance and a change in velocity, and of course change in velocity, the easiest way to say that is delta V. Okay, and then the force and the distance gives you work, right? And so that change in velocity means that I have a change in kinetic energy, and that's where this thing comes. It comes straight out of conservation of energy. I don't get anything for free. If I want to change my velocity, I've got to pay for that by doing some work, and I don't lose it. It's all still there. All right, check that out, and we'll talk about that in recitation and do some of those problems. Here's a little picky point here. If a force does work to move an object in the path, doesn't matter. That's what we talked about at the beginning. If it's the same amount of work any way you go, it's called a conservative force. And then here's some examples of non-conservative forces: friction, air resistance, drag. Any of those things that would seemingly steal energy away would be called non-conservative forces. If I take a box and I put it on ice, and the friction is very, very low, we could say 0, and I put a force on that thing, and it moves over here some distance x, and I calculate the work. On the ice, the friction is 0, so it doesn't matter which way I take it, and in a frictionless environment, all that force would be a conservative force, and it's path independent. Okay, if I put friction in here, though, if I come along and say, well, let's put this box on a table or on the rough concrete sidewalk and slide it. Now the thing's not moving as much as it would seem to, and that friction stole some of the energy away that would have been in the kinetic energy. Okay, that still doesn't violate conservation of energy. Conservation of energy says it's all still there, and it is there. When you have friction between two objects that are moving, it slows it down. So I do lose kinetic energy, but it goes into another form, heat. Right? If you take two hands and you rub them together, then you're generating heat right there, and that friction always leads to heat. So the energy is still there. The law of conservation of energy is still true. We just have to include another form of energy, thermal energy or heat, to make that work. All right, we're getting close to the end here. Power is an important idea. You can either think of it as the rate of work, which would mean that power equals work divided by time, or the rate of energy. How fast am I using energy? And that would be energy divided by time. If you see anything that talks about power, just go ahead and write this guy down right there. Power equals work divided by time. All right. In the picture here, the girl's going up the stairs, and let's say that it's going to take her 400 joules of energy to go up the stairs. Okay. Whether we calculate that using the work to go upstairs, or if we say once she's up there she has a potential energy of 400 joules, doesn't really matter. It's the same thing, right? As she goes from here to there, she's got to put a force, she's got to move a distance, and the work all gets stored as potential energy. It's the same number. The question now is, how fast does she do that? If the time is 10 seconds, then I'd come in here and say the power equals work divided by time. That's 400 joules divided by 10 seconds would be 40 joules per second. And here's one more unit that we change up just because we can, and we call that a watt. Okay, so she just used 40 watts. Well, her power was 40 watts. If she had taken 5 seconds to climb the stairs, she would have been working a lot faster. 400 divided by 5 would be 80 watts, right? So she, in order to go up the stairs in half the time, she'd have to have twice the power. And that's all we're trying to do here, say how fast are we doing work, or alternatively, how fast is she burning up the Cheerios she had for breakfast that gave her the energy to, you see where this is going, right? Okay. We abbreviate that capital W, 40W, like that. That is the same watt that's on your light bulb at home. So when your light bulb says 60 watts, then what it's really saying is I burn up 60 joules of energy every second. Or alternatively, the power plant has to generate 60 joules per second to run that light bulb. Okay, work or energy, back and forth, same thing. Okay, it's not the same thing, but they're related. This is for 221 here. I'll say just a couple things about this. We said if you have a changing force, that I could take the amounting of force and multiply by the displacement. If it's not changing, if it's a solid, an even amount of force here, and it moves from here to there, it's this much force and this much displacement, they're using D, whatever, then the work would be force times distance. That would be the length times the width of that rectangle, and I would have the area underneath that rectangle. Okay, so that's not a changing force, that's just a solid, and we'd multiply the two, no big deal, but we do get that area underneath the curve there. Well, calculus is all about finding areas under curves, is one thing that calculus is really good at. And sometimes we cut little boxes, and we say, well, I've got this box, and then I've got that box, and I add up each of these rectangles because those are kind of easy to find. You can see that you could even do that over here. If I made a box and found this, and then found the next box, and kind of cut that into slices. And so Isaac Newton 400 years ago said, hey, we could actually he said I could do this, right? He invented calculus and locked it up so nobody else would have it to solve the problems he alone could do. But finding the area underneath that curve is an important thing to be able to do, and that's what this symbol right there means. Work equals the integral of force with respect to x. It's a way to add up that area underneath there. So don't worry anything about that. That's just kind of a freebie there. Work is a very important idea. It's a very simple idea. We have to pay for whatever we get, and that conservation thing says you never get anything for free. And so with that, that would be a huge idea in physics. It doesn't matter if you're talking about the energy of a star, which goes down and turns into grass, which turns into a cow, which we eat to be. But energy equals energy at any 2 points you want to pick. Generally, that would be the potential energy at point 1 plus the kinetic energy at point 1. And same thing over here. And in my opinion, at this level, it's easiest just to kind of go ahead and get a rubber stamp and put this on every problem that you see, especially if you have one object at 2 points. And I'm thinking about a roller coaster at the top and at the bottom. I'm thinking about a hammer that gets dropped off of a roof, right? It's at the top. It's got a certain potential energy, kinetic energy. When it gets to the bottom, the sum has to be the same. So that's a huge idea. And then, you've got work equals force times distance. You've got the kinetic energy equals 1/2 mv squared. You've got gravitational potential energy is mgh. You might need the spring potential energy, so I'll put it here, 1/2 kx squared. You had power, work divided by time. And those are the ideas that we're playing with in Chapter 7. All right. Hope you enjoy it. And bring your questions in next time, and we'll see what happens. Thanks.